Welcome. Today we discuss volume. First, we want to derive a nice volume formula for computing volumes of solids. So we have the setup is like that. We have a x-axis and we have some solid which is here given on the interval AB. And what we know at every x, we know the area of this slice, of this section here. Let me just maybe draw that a little bit so that we here see the surface. And here is a slice. We slice the solid at the position x. And what we do is we kind of make that slice a little bit thick here, and the size is just dx. Here the thickness is dx. So what we obtain here is a slice, and we have here, assume we have the area is known. AX is the area of the cross section. Now, if you multiply with dx, we get the volume of a small slice. And then we just sum up over all these possible slices, and we go, of course, from A to B. And that's the volume. So this is our formula which we are going to use today. Area dx times dx gives the volume slice. We integrate that up. Okay, that was section 1. Let's look at the cone. And let's assume that the radius, so it starts at 0, goes to 1, and we assume just that the radius is just equal to x. If this is x, this is also x here. So in this case, this is the slice here. We can compute the area here. So the area A of x, of course we know if that's the radius, r squared pi, that's x squared pi, that is the A of x, and we have just to integrate now from 0 to 1, A of x dx, which is the integral from 0 to 1, x squared pi. We know how to integrate that, right? So this is x cubed pi, it's just a constant from 0 to 1 times pi, and that's just 1/3, that's just pi third. So this is a formula which already Archimedes, who we see here, has already known. And let's just do that a little bit more general. So I want to do something similar, but it doesn't have to be a square section. It can also be a pyramid. So here we see a pyramid. Let's just put it upside down here, and let's just draw this pyramid. And again, we can do the same thing. Let's make a nice formula here. Let's assume that is, again, that's x, and we know the height is h, and maybe we know that this side here kind of is 2a, so this is half of it, like here in this picture. This is a here, and we know all the formula for a pyramid. It's the base area times h over 3, but let's use calculus to derive this. So what we have to do is this is x here, we have to get for every x, we have to get the area of this slice. So we cut it up at height x, and we look at the area here. We have to get a formula for that area here. What helps is that we don't draw in 3D, but we just draw in 2D. Kind of, this is A, this is H, and this is, if this is x here, the whole thing is H, and this is x, and then we can get the radius R. We can get the radius R. R is equal to, so it's just H and then scale it times x over, what do we have? We have A times x over H. So this is the relation, and then we know A of x is just a square times, just a 4 times, it's actually 4 times, right, because we have here, we have 4 such thing, it's 4 times this squared, A square x square over H square. So that's the area of the cross section here. A has been now replaced with A times x over H, and we square that, then we get the area of one of the pieces. We multiply by 4 so that we have the whole area. And now we can integrate, right? We integrate from 0 to H. 4, let me just take 4a squared over H squared out, x squared dx. And again, that's the same integral which we have seen here. And so this is x cubed third, evaluated at h gives h cubed third. So this is 4a squared over h squared times h cubed third. And the h square cancels here with the h square over there. And what we get is 4a squared times h over 3. That's the formula, which you all know, right? It's the base area times h over 3. So the volume of that pyramid is the base area times the height over 3. And we have now proven that using calculus. Okay, now we come next. The next section will be the sphere. Very exciting topic. Let's take a sphere of radius 1. And I just put the x-axis here. So this is x here. And so what we have is, we have to figure out what is the cross-section area. So this is from -1 to 1. And we have to figure out this cross-section area at height x. So we have a little slice here. So we have to find that this is dx here, and we have to get the area. Let me just, I don't have a sphere here, but what we are doing, we are cutting the sphere, right? And at height x, what we want to know the area of that slice, and then we make a very thin slice here. Let me just make that here. So this is a thin slice of the sphere, and this is dx, and this is the volume of that thin slice. And what we do eventually when we integrate, we take all these little slices, right? We take all these little slices, and so all these little slices here, we add them up, and that gives us the volume. They're also delicious. So let's just do that here. So again, it helps to actually kind of make a picture here. What happens is x, and that's the radius which we want to know, and this is 1. This is the radius of the, right? This is the radius of the sphere is 1. This is a right angle, and we can use Pythagoras to get r. So r is equal to the square root of 1 minus x squared, and the slice area is pi r squared. We have computed the area of the circle last time. So what we have, a of x is 1 minus x squared times pi. And now we can integrate, right? We integrate over the whole apple or the whole sphere here from -1 to 1, 1 minus x squared pi dx. And this is no problem to compute. So this antiderivative is x minus x cubed third, evaluated from -1 to 1 times pi. And if we evaluate it at 1, we get 1 minus 1/3 is 2/3. We get the same 2/3 here. So this is 4/3 and 4/3 pi. So this is the volume of the sphere. I just want to tell you a little bit about Archimedes. So Archimedes was the first to compute the volume of the sphere, and he was very proud of it. He even put that formula on his tombstone, even so the tombstone has not survived. So he was killed during a Roman invasion, and so while doing math, and actually just in the moment of doing math, as depicted. As shown in this picture. But I want to tell you a little bit about how Archimedes thought. Archimedes didn't know calculus, but he had kind of a great idea. So what he was doing is he was comparing the cross section. He was comparing it with a complement of a cone. So what he was actually thinking is, so we have talked about the cone before. So he took a cone of the same size here, and so the radius is 1, and so he embedded the cone in a cylinder. And now what happens at height x here? So at height x, the area of the, so this area here, which we have here, is pi x squared. And the area of the entire, the area here of the slice of the cylinder, of course, is pi. Pi 1, the radius is 1. So the area here, which I'm kind of drawing here, kind of this annulus area, annular area here. So this area here is the total area of the cross section of the cylinder, which is pi, and then he subtracts the area here, pi x squared minus pi x squared, and that's exactly that, right? So this is the same thing. This is the same thing than that. So he got the same slice, and if the slice is the same at every height, what happens is also the volume will be the same. So he got that formula by just subtracting the volume of the cylinder, which is pi, minus, and then he took the volume of the cone away. So cylinder minus cone. So this is pi minus, and we have computed pi third last time. So this is 2 pi third. And this is the half sphere, right? Because he compared it with a half sphere here. And then there's another half sphere. And then this is a half sphere. Very historical computation. And the next thing we are going to compute the volume of a lemon. So let's model a lemon. I have here a lemon tree. That's the pride of our household here, this lemon tree. And so let's just model it with the sine function. So what we take here is we take sine of x, the graph of sine of x, and then we rotate it around, right? From 0 to pi here, we rotate it around, and so this is our lemon. So what we have to compute is we have to compute this area of that slice. And here the radius is already given, right? The radius is actually just sinus of x. So r is just equal to sine of x. And so the area A of x is just pi sine square x. And we have to integrate from 0 to pi sine square x. Before we do that, maybe you can think while I'm talking here a little bit about this lemon. This is actually a lemon from last year. This sucker doesn't want to grow up completely because it knows that if it is growing up, it will be sliced in pieces. You see, the new ones here. The new ones are already coming, and they are a year behind that guy. But we have no mercy. So I've no mercy. Actually, this is the moment this guy is going to die, and so we can make some lemon juice. So that's the lemon, and I'm just cutting it here. That's the end of it. Isn't it beautiful? And so we have a little slice of that lemon. So and we can make lemon juice. It's very easy to drink the lemon juice. You just need the slice. So this is the lemon, but we have to bite into a sour lemon to actually compute this sine square x. And I hope you still know how to do that, right? So there is an important identity which we can use to integrate that, and that's the double angle formula. So it is sine square x. I hope you know it. So there are two formulas. One is for the sine square x, which is 1 minus cosine 2x. And then there is also cosine square x, which is 1 plus cosine 2x over 2. Also called double angle formulas. I actually think these are the only formulas which you ever need to know in trigonometry. Because, for example, it gives you sine square plus cosine square is equal to 1, 1/2 plus 1/2, that cancels away. Or cosine square minus sine square is cosine 2x, or you differentiate it and you get the double angle formula for sine x. These are very, very important formulas because we often have to integrate sine square x here. So that's what we do here. We integrate sine square x by just replacing sine square x with 1 minus cosine 2x half. So what we have is pi, and then the integral from 0 to pi, and then we have 1 minus cosine 2x half dx. So we have not yet integrated, but we know how to integrate 1/2, right? So this is equal to pi, and then 1/2 is pi. This is equal to x half. And the cosine 2x we also know how to integrate, right? That's sinus 2x over 2, and we evaluated this from 0 to pi. When we do that, this falls away. This is 0 both at pi and 0, but here we get just pi. We get just pi half. Pi times pi half, so we get pi square half. So the volume of that lemon is pi square half. Okay, one last example before we wrap it up. This is the solid here. So let's assume this is the x-axis, and let's assume maybe we go from -2 to 2. And what we have here is we have a relation between x and the radius, and I just give you that. So that's given as the square root of, so this radius here, the radius is just the square root of 1 plus x squared. The reason why this is called hyperboloid is because if we just square both sides, we get r squared minus x squared is equal to 1, and we get a hyperbola. So this is a hyperbola. That's what we actually see here. We see this hyperbola. But for us, what we are interested in is the area of the cross section. Right? We take a cross section here at x. So at x here we compute the area. And what we get is, of course, we got pi r square here. Pi r square, square root of 1 plus x squared squared, which is pi times 1 plus x squared. And now we integrate from -2 to 2 to get the area pi 1 plus x squared dx. No problem to integrate again. So this is pi x plus pi x cubed third. And we evaluate this from -2 to 2. So when we evaluate it at 2, we get 2 plus 8 third, which is 14 third, and then the whole thing times 2. So this is 14 third plus 14 third. This is 28 third. Maybe a little bit bigger than 9 for this solid. That's it for today, and see you tomorrow in class.